There we go. So, does anyone have any debate or contention with McKay's table? We're like, hey, that's not what I got. We all good with this idea? So what was the story? The candy was continuing to double. Now, I want to point this out. So day 6 would be 32. Day 7 would be 64. Man, and we even see a graph over here. Let's look at this graph. We see the same pattern of continuing to multiply by 2, right? And then when I look at this graph, does this graph make sense for this idea of repeated multiplication?
Yes.
Yes. Why? It's a geometric or exponential. Notice the only time we should ever get a linear function is when it has what type of rate of change? Additive. And so if you're repeatedly multiplying and you get a line, we know we made a mistake there. And I know that this is the most common mistake, so please hear me very clearly on this. If you made that mistake, I get it. But please notice, if I were to make this graph, and I were to do this. Okay, so day 1 was 1 candy, day 2 is 2, day 3 was 4, day 4 was 8. That'd be pretty darn linear, wouldn't it? Yep. So what's the issue with a graph like this? Well, I mean, if we look at the table, is it doubling? Yep. But what is the issue with this graph?
It's supposed to be 6 up there, or down by 2s.
So when you say going by 2s, like we see here with Zay's, we should be, what was it? Did you put this graph up here, Zay?
Yep.
Okay. With the graph, we should repeatedly what when we scale?
Go by 2s?
Not necessarily just by 2s, but what is he doing to go from 2 to 4 to 6 to 8? Adding, right? 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. Whenever you scale, you can add whatever you want to go by, but your scale should always be an additive rate of change. If it is not an additive rate of change, it will mess your whole graph up. Notice with this scale, you see how I'm multiplying? And it created a linear graph. It shouldn't be linear. It's not an additive rate of change. So that's what we need to be aware of.
True.
Okay? Now, we started to model it. We've created a table. We've created a graph. But now, we're asked on number 4, use your model to predict the number of candies that Augustus would earn on the 30th day with this plan. And I saw some people go ahead and make a recursive here, which is another type of model. When I'm using that recursive, f of n equals f of n minus 1, and then what? Times 2. Say again, sir? Okay. Now I will point out we do need a starting point. So f of what equals what? Okay, so on day 1, he got 1 candy, right? That's a good starting point. However, if I want day 30 here, that would be 30 minus 1, or 29, times 2. Do I know how many candies he has on day 29? No. Remember, does a recursive allow us to jump really far into the future? No, it just lets us get the next one. So what could I do, though, to continue to figure out how many candies he has on day 30?
Keep adding, so.
Keep what?
Keep multiplying.
Keep multiplying, right? Is it possible, gentlemen, are you focusing so you can learn? So is it possible to continue this table all the way out to day 30?
Yes.
Do you want to do that?
No.
Very quickly, you're like, no. Remember, this is why we like explicit equations. Explicit equations are not there to make your life harder. They're actually there to make your life easier. Okay? Explicit equations are there to make your life easier, but that's why we need to learn how to write them. Now, there's 2 things I do want to point out. Did you know that you didn't have to go by 1 day when it comes to this table? notice, to go from day 1 to day 3, what could I have multiplied by? 4, which makes sense, because I'm multiplying by 2 twice, right? So if I got to day 8 and knew it was 128, could I then jump to day 10? What would I multiply by to get to day 10? Not 2, 4. Could that speed the process up for us a little bit?
True.
A little bit. But notice that's why it's a common ratio, so we can actually figure that out. Notice, heck, could I go to day 5? What would I need to multiply by to go to day 5? How many candies were there on day 5?
16.
And I started at day 1 with
1.
1. So, how about 16? Right? Now notice how that's 4 days. What's 2 times 2 times 2 times 2? 16. Notice how there's patterns there. That means I could also even go by 5 days. What am I going to multiply by on the candies to go 5 days? 32. So I could get to day 2, which is going to be, does someone help me out with this? 532 maybe? Someone check that? No, 480, 512. I think that's right. Day 10, no, it's 128 times 4. I think it's 512.
No. 480.
It's 512.
128 times 4?
It's 512.
It's an 8, yeah.
It's 512.
512? So now I want you to notice, it doesn't have to go by individual days. If we're paying attention to these patterns, now I know I can go to day 15, go by 5 days, and what am I going to multiply by to get to 5 days? Every 5 days was how much? 32. Right? Could that speed the process up a lot?
Sure.
You talk about not wanting people to clown you, yet you clown me all the
I'm asking a
time.
question, man.
I'm
You
teaching.
All right, go ahead.
So we can use that to speed these things up. Mathematics is a structure of patterns that can speed everything up for us. So I can go by 5 days if I recognize what it means to go by 5 days is to go by 32. All right? So let's use this. What is 512 times 32? 16,384? You think Augustus is getting less candy this way?
No.
No! Right? Which I want you to understand that should make sense. A multiplicative rate of change should be more than an additive rate of change. When you repeatedly multiply, doesn't it give you more? Yeah? So what about to get to day 20? Multiply by 32 again, right? I think it's some massive numbers up in here.
Yeah, you're in the 500,000.
500,000? 500 what?
24,288.
What about day 25? Oh my gosh.
16 million.
16 million? What's after that 16 million?
777. 266.
And then day 30. Well, we wanted to know day 30, right? So let's finish it out. Yeah? 870? So, huh? Yeah. I want you to know, did y'all get the same answer? Okay. So I want y'all to notice, like, a multiplicative rate of change, that's huge, isn't it? It changes by a lot. These are structures that we should pay attention to. All right? So I want you to notice though as well, like if we learn how these patterns work, we can actually learn how to make them work more easily. Because I would agree, I don't want to go from day 1 to day 30 going by ones. That would suck, right?
Yeah.
But if I learn, hey, 5 days is 32, then I can just keep going by 5 days from there on out. Gentlemen, why are we putting our stuff up? We still got 4 minutes left. So now this brings us to our explicit equation. We already got a recursive. Y'all, this explicit equation is important. You need to pay attention to this. I want you to remember earlier when we did the plan on number 1, remember how we ended up writing the equation, hey, he's starting with how many candies? 10, right? And what's he repeatedly doing to it? Adding 10. How do we show repeated addition? By the way, don't forget, this is number 2. By multiplying, and we did n minus 1 because it started on day what? Day 1. Let's look at this problem. How many candies is he starting with? He's starting with 1 candy. What is he repeatedly doing to that 1 candy? Doubling, so meaning we multiply by. But Donovan, how do we mathematically show repeated multiplication?
Exponent.
An exponent. And that exponent needs to be a what? Variable so that it can change. And this is very close to being correct. Does anyone know what we're missing? Kind of. I want you to think about it. If I plug day 1 into here, what's 2 to the first? 2. What's 1 times 2? Notice, is that day 1? No, that's day 2.
Minus 1.
If I do minus 1, what is 1 minus 1? 0. 2 to the 0? 1. 1 times 1 is? So if I do this equation, does it work for this table? If you check f of 30, what is 1 times 2 to the 30 minus 1? Any guesses?
30 bill, 530,870,912.
It should be that 536,870,912 that we got. Is that what you just got? Notice, if we understand how these equations work, we need a starting value. We started with 1 candy. What did we do to that candy? Multiplied by 2, n minus 1 times. The nature of these equations are born out of what we're mathematically doing. We're multiplying by 2 repeatedly, so we need an exponent. We will wrap this up tomorrow. Tonight, your homework is 1.7, the ready section, numbers 3 and 4, and the go section, numbers 16 through 18. I would either circle it right now, or I would take a quick picture of it.
No, that.
Oh, we'll give him one better. What you guys say? You said you was doing it.
Especially if I've already sprayed your desk and put a paper towel down, do not forget to wipe it down.
Okay. Take a picture of that.
Hey.
No more words.
Yes, sir.
Screw.
Okay.
Huh?
Say again.
Okay.
Hold on 1 second, Alan. I need to know here. Is Jamari being real or is he just trying to play around so much? I mean, I hear you on that, but I'm not saying, like, I mean, I get that's how it is. I'm asking, like, does he actually need to go? Yeah. Okay. Huh? Yeah, I got you. Get on out of here. Thank you for asking that. Yes, sir. So if those from previous lessons?